As you see, I changed the way the course is. I was planning to talk about quantum cryptography today, but then I decided to talk today about classical typical. Actually, I was decided to talk about classical and quantum typicality today, but then I thought, no, this is too much. Let's talk about classical typicality today, and then a little bit lighter in the second part of the class, and then tomorrow we talk about quantum typicality, and then something lighter after this, maybe quantum cryptography, and then on Thursday we talk about quantum algorithm. Okay? Why I decided to talk about this? Because some people were asking me about these things, and this is the fundamental thing behind all information theory, classical and quantum typicality, which means that we are this property is what is called it has the name asymptotic equipartition property, both in quantum and classical. And asymptotic means that it's the asymptotic regime. So we are in the regime where the information source emits infinitely many messages, and each message is infinitely long. So that's asymptotic theory. Equipartition because in this regime, Shannon realized that the set of all possible sequences can be split into two. One of them that are overwhelmingly likely to be emitted, and the other set overwhelmingly unlikely to be emitted. And then when he realized this, he was able to prove the theorems. So this property, which is fancy name for the law of large numbers. It's just this, the law of large numbers applied to probability distributions. Lies in the basis of the proof of both data compression and channel capacity. So that's why I decided to talk about this thing in a little bit more detail, because once you understand this, you have all the tools to prove the theorems. So it's not difficult to prove once you understand why this happens. So, typicality is a fundamental concept that appears not only here, but every time that you have a huge number of things, this thing happens. Every time. For instance, if you have a huge, let us say, a many-body system, and or a quantum system with many degrees of freedom, you pick up a quantum state randomly from the Hilbert space, which is huge, this state will be typically entangled, which means that the space of non-entangled states has measure 0. The other thing, if you have if you pick up a quantum system Hamiltonian with many energy eigenlevels, you pick up a small set of observables of this guy and compute the expectation value of this guy, or any observer of these guys, and take the limit of infinite time in every eigenstate of energy that's compatible with the macroscopic energy, this will be a thermal state. So the energy eigenstate will typically behave as thermal state. This is one thing called the eigenstate thermalization hypothesis that tries to explain why things thermalize. So typicality appears everywhere, and there is a huge difference between classical and quantum typicality. So today we will talk about classical typicality to understand what this thing is and why they appear, and what are the properties of these sets that allows us to do these statements. So as I thought, this is asymptotic equipartition property, which is just the law of large numbers. It's nothing more than this. So, and this was what Shannon realized, that I can split the set of all the sequences, except when the probability distribution is uniform. Then you cannot do anything. then there is no compression, no channel capacity, nothing. You are lost in this case. But usually this guy is not uniform, so we are good. Let me give you an example that I did yesterday night. It's easy to compute this in a computer. I just pick up a random variable, binary random variable, and choose the probability 3, 4, that puts 1, and 1/4, that puts 0. I think that was this. For some reason, I think that I did the plot with this exchange, but the result is the same. It doesn't matter. It doesn't matter. It's just, it's not uniform probability distribution. So then the sample entropy of some sequence would just let this source of information here, which is a random variable, emit any bits. And then we compute the sample entropy of this guy. The sample entropy is just the information that we have upon learning that sequence. So it's just the probability of, I just counted the number of ones that it have in the sequence. That's the probability of getting 1, yeah, with P, 3, 4. And then I took this to the power of the number of times 1 appears in the sequence of length n. Okay, this is the probability because I don't care about the order of these guys. I just care about how many ones we have in the sequence. And then this is the number of zeros that appear there, and that's the probability of zeros to the number of zeros that appear there. Okay, because this guy must sum to n. Okay, and then this is the sample entropy of the guy, of each sequence. And this is the entropy of this probability distribution, channel entropy of the source. I just computed it here, is approximately this guy here. Okay, then we have the sample entropy and the entropy. Then we go to the typicality. Typical sequences are those in which this guy approaches this guy, which means the sample entropy, the information of the sequence, is approximately the same information as the source. So that's the idea of typicality. And typicality says that it's highly likely for in the limit of infinite n of the source emit a sequence in which this guy is equal to this guy. That is what we call weak typicality. By the end of the lecture, I will state the strong typicality, which implies this, but just the weak typicality is enough for us to prove Shannon theorem. The weak typicality says that this guy converges to this guy in the asymptotic limit. And you see that this is true. That's just a simple plot, where I plotted here the sample entropy minus the entropy, the Shannon entropy, which is just a number. And this is the length of the sequence. Okay, I should increase this letter here, but that's okay, this font here. But this is 10,000. So I just generated random sequences using that probability distribution and computed this guy and take the Shannon entropy. And you see that we have huge oscillations when the sequence is very small, but then this rapidly converges to the sample entropy. Yeah.
So for each point you plotted,
yeah,
you have one particular random sample? Or
yeah, exactly. Okay. No, this means that, let us see, n equal 3. I just generate one sample, I don't know, and computed the sample entropy of this guy and compared it to the entropy. But you see that when the sequences are small, we have large deviation. But then this rapidly converge. Well, not that fast, but if you have really convergence here, this guy will decrease. If you have I don't know, 10 to 5, 6, 7 here, then this goes to align. You can easily do this in any software. This is very fast actually, the convergence, and you see that these guys really converge to each other. So this means that since these sequences are being emitted randomly, this means that the source is highly likely here to emit a sequence in which the sample entropy is very close to the entropy of the source. So this actually happens. This is not, just for binary distributions. It happens to every distribution. But binary distribution is easy to do. But you can test with Gaussian or whatever distribution you have in the computer. So that's the notion of typicality. That's the meaning of typicality. And this happens when the size of the thing increases too much. And this is because of the law of large numbers. That is a non-intuitive law, at least for me, but it works. It really works. You can do these tests very easy in every computer, and you convince yourself that this is true. So, let us define what we call weak typicality. Weak typicality, as I told you, every physical system can be described by a random variable, which is just a set that we have an alphabet and you have a probability distribution associated with this thing. It doesn't matter what this guy is. And we call the letters A, the letters of the alphabet. It doesn't matter what they are also. We simply don't care about these things. And this hypothesis is extremely, extremely important. Without this, forget, you cannot prove anything. Let us go to here. So this is proved under this assumption, which means that the random variable means this. The random variables, we have a sequence of random variables because we needed to go to the asymptotic limit. So we let the source emit a bunch of sequences, a bunch of symbols, in such a way that this n is very huge. In the end, it goes to infinity. And every one of these guys is a random variable that is emitted with the same probability distribution and independent from each other. So it's like throwing a dice. Every time I throw a dice, I get a number, and if I throw it again, and they are independent and equally distributed. So that's the sort of system that we are talking about. So we just name the sequences small x over n. This is just a sequence, is the one that I used to compute the sample entropy in the last slide. One sequence is that one realization of this random variable. So this is not x to the power of n, it's just a notation for a sequence of n random variables. Okay? So, the probability of a particular string is this guy. We computed this, I think, that in last Friday. Yeah, I think last Friday I showed this to you. Friday or Monday, I don't remember, but it's there. That's the joint probability of every symbol to be emitted. But since we are doing this hypothesis here, IID, then these guys factorized like this because they are independent of each other, so the probability is just multiplied. And then, since they are equally distributed, each one of these guys has the same distribution of the source, the same probability distribution of the source. This is the meaning of that hypothesis. And then we simply can write it that way. This makes things much more easy because we need this probability. So this thing is easy, and everything here we compute using logarithm functions. So it's just summing up things. That makes things much more easy. Okay, so now intuitively, at large limit, we expected this to happen. But what is this? Remember that we call the letters of the alphabet AI. Okay? It doesn't matter what they are, but they are symbols. It doesn't matter. So this is the probability of when n is very, very large. We expected that the letter AI will appear a number of times that's n times the probability of AI. That okay? I mean, I'm expecting this is the definition of probability. You know, I expected that in an infinite, like a fair coin. If I throw a fake coin many, many times, I expected to see half of the times 1 and half of the times 0. So this is just what's written here. So it's the number of times that it appears. N is the length of the sequence times the probability of that letter to occur. So we expected this. This is our intuition behind probability. That's the way actually we compute things in every physical experiment. We assume that this holds. That's why we have to make a bunch of measurements in the experiment. Oh, sorry. That's why you have to make a bunch of measurements in the experiment in order to define probability. Because of this property. So, and that's the sample entropy, is the information that I have upon learning one of the sequences. Okay, is this, I mean, the log. Remember that we define an information as the log of 1 over the probability. Because Shannon defined information as the degree of how surprised you are when the thing happens. So it's the inverse of the probability. That's why we have minus the log of the probability. That's the information content of everything that happens. So this is the information content of that sequence. When you learn that sequence, particular sequence, you learn this amount of information. So this is just normalized information that you get from this, from this thing. And since it is, we expected this. And this guy can be written like this. We just have this guy here, which the probability, this is just the Shannon entropy of the source.
It is exactly, the first point is exactly the typicality, no?
Wow, no, because this is the frequency. This number is not exact.
No,
Because
it's not exact, but
it becomes exact in the infinite limit. Yeah, because if I throw a fair coin 10 times, I will not get 5 times 1 and 5 times 0. I can get 4 times 0. And actually, when I was running
But the fact that you will have something around this number is precisely the definition of typicality.
well, yeah, precisely that the
So
equality
this is-
here is typicality. Yeah, but this only happens when we go to infinite limit. Yeah, then is equality. One thing, if you try to do that plot that I showed to you in the computer, put some if conditional there, because I mean when the sequence is small, I got all zeros, and then the logarithm diverge, and then the program stops doing calculation. So, yeah, because it's possible, but this doesn't happen when the sequence is large. So this is intuitively what we expect. And then we define the sample entropy like this. That is the thing that I just computed. Okay, is that okay? Because once you understand these things, then you understand all Shannon theory. Because everything is based on here. And then you see that, this only holds when this guy is very large. Think about it the way we define probability. We define probability as frequencies. Or we can use base interpretation, but this is a different thing. But we usually define probabilities as frequencies, which means that we count the number of times this guy appears and divided it by the total number of times that you run the experiment. This is done everywhere. in quantum computers, in physical experiments, everywhere. But this only converges to the real probability at the infinite limit. Actually, there is a hypothesis here also that I didn't mention, which is important, that we assume that there is a probability distribution underlying our experiment. Which means that we assume that when we are running a quantum computer or a physical experiment or whatever, they are the same actually. We assume that there is a real probability distribution and that these guys converge to this. But in classical probability distribution, this is called the Kolmogorov extension theorem. Kolmogorov proved that indeed there is this probability. This probability exists. Proved the conditions for this to exist. In quantum physics, we don't know. There are some attempts to prove the Kolmogorov extension theorem to quantum physics, but there are no satisfactory proof until now, as far as I know. So this is a hypothesis that we assume. Let us assume that there is. The probability distribution exists there behind all of this. And then we make discrete measurements, we can actually get closer to this probability distribution. But this is a side thing. So we define the sample entropy of the system, which is the information contained in every sequencing. That's the meaning of sample entropy. And we state that this guy converges to the real entropy of the source, which is the average information that you have upon learning any message emitted by the source. These things converge. This is typicality. Okay? Then we properly define it. Xn is a delta typical sequence if its sample entropy is delta closer to H, which means that the difference that I plotted there between the absolute value of the difference between the sample entropy and the true entropy is smaller than delta. Delta is a number, is a positive number that can be as small as you please. Okay? That's the definition of typical sequences, and that's the definition of typical set. So it's a typical set which we represent by this symbol here is just the set of all sequences in which this happens. All typical sequences. And the law of large numbers said that when n goes to infinity, this is overwhelmingly likely. That's as we saw in the example that I showed. So this is a classical typicality. Oh, time flies. Okay. These are the properties of the typical set that we proved in the second lecture, I think. If I'm not mistaken, we proved this thing, not for the other distributions, but for this we proved it. The typical set asymptotically has probability 1. This is extremely important because when you go to infinite, the probability of the source to emit a sequence that belongs to the typical set is bigger than 1 minus epsilon. For any epsilon in this guy and any delta bigger than 0. So it means that the source will typically emit a sequence in which the sample entropy is very close to the true entropy of the source. And this codifies in certain sense the error. This guy depends on n, because when n goes to infinity, this guy goes to 0. And the probability converges to 1. So that's why we say that in the infinite limit, the sample entropy converges to the true entropy in probability. That's the meaning of this sentence. This guy goes to 0. Okay? What?
I think I understood the idea, but I don't understand.
But you understood or not?
Yes.
Okay. So that's the first property. That's not difficult to prove. I mean, we proved this a few lectures ago, but exponentially small cardinality. which means that this is a very important thing because without this, we don't have data compression. If this wasn't true, a data compression theorem would not be possible. That's because it simply sees that the total number of the sequences, the typical set, the typical sequences, which means the cardinality of this set here, is exponentially smaller than the total number of sequences. That was Shannon's idea, because Shannon said, oh, since we have these, the unity probability, the typical set has all the probability, which means that the source will always emit a sequence that is there in that set. And that set is exponentially smaller than the total set of sequences, then I just needed to compress this set and throw away the rest of the sequences. Since the source will never emit that thing, that's okay. I will never lose information. And then it's easy to prove that the cardinality is bounded by this number and this number. This number is very small, so this number is closer to this number. Delta is small, so this number is very closer to this number. So the cardinality is bounded from below and above, but it's a number, basically. So this is the size of the typical set. We can think of the size of the typical set as 2 to the power of n times the entropy. And you see that the entropy, if you have a uniform probability distribution, this guy is exactly the log of dimension of the system, which means the number of the sequences, which means that is equal to this guy. So you cannot compress. The typical set is equal to the entire set.
It's exponentially smaller because this is also exponential, no? But with
but exponential. But these guys, yeah. But the number of sequences is this guy. No, yeah. And this is age. And age is.
I agree with this, but it's still exponential.
No, it's exponentially the number of the sequences, but exponentially smaller than the number of total sequences.
But when you have two exponential,
well, you have a bunch of sequences. That's true. The typical set has a bunch of sequences, but if this guy is not uniform, you have an exponentially smaller cardinality, because you divided this guy by that guy over here, you get much less sequences.
Yes, but this is a polynomial, not exponential suppression, because this is.
Oh, it's
I mean,
exponential,
imagine
no?
that you have just 1/2, no? Just this will be the square root of the total number. It will be divided by 2. So it's a constant in the exponent. As this is a constant in the exponent, this will be something that is polynomial, no?
I'm not following, because
Maybe if you just look at the percentage of typical sequences, you will see that exponentially the case.
divided one by the other, you see the range of this guy, and it decays exponentially. It's better to talk in the microphone. Yeah. Yeah.
I think when you decrease the order in an exponential, that's considered an exponential.
An
decrease.
exponential, exactly.
Yes.
Exactly. An exponential. In the number, because this is the number of sequences that you have. I don't know, you guys are much more expert than me than exponential decrease and polynomial decrease and things like this. But for me, this is exponential decrease because of the fraction. The fraction decreases exponentially with the entropy. Miko is not convinced yet.
I understand what you mean, but so what happens to me is that if you have just the square root of the number of sequences in your typical set, it's a square root. This will be, but it's still exponential, and you have. It's true that when you divide this, it's an exponential. But it's just a question of how you understand the advantage or the.
Yeah, I don't know because I mean,
understand, but I understand your point. It's not-
just like they said, it's just when you look at the fraction, it decreases exponentially with the entropy, and or increases exponentially when you increase entropy, and the entropy goes to.
But what I mean is that depends on how you understand, because if you have n and square root of n, or square root of n divided by n, it also decreases with the n. But for me, this will be some kind of polynomial.
Polynomial.
But
Yeah.
I mean, I understand what you mean.
Yeah.
That this goes to zero exponentially. It's,
Exactly. And then from this, it's easy to prove the E part of the AAP, the asymptotic equipartition property, which is just the probability of each sequence in the typical set is bounded from below by this guy and bounded from above by this guy, which is basically the same number. So the probability of each sequence in the typical set is emitted asymptotically with the same probability. So that's why these properties called equipartition, asymptotic equipartition property. Equipartition comes from here, the equal probability. So every typical sequence has exactly the same probability of being emitted. So that's the main idea behind the asymptotic theory of information. With this thing, we can prove data compression, just with this result. This is a data compression. We discussed it, I think that Friday. And this is very easy to prove data compression with this guy, except the converse theorem. The converse theorem is not that easy because you need some entropy inequalities and things like this. The converse theorem shows optimality. Data processing, the data compression shows that there is a code in which you achieve compressing of information with this rate, okay? And then this is just, a picture of this guy. So the entire set of all sequences can be split into two. And one of them is the typical set with this size, this number of sequences, and all sequences are this size. Okay, that's the entire set. That's the main idea behind the proof of this thing. Then, as I told you, the Shannon compression theorem, with data compression, which basically says that we have a sequence here, and then we have an encoding, and then we have a channel that just send the information to Bob to decode, and then he gets again the same sequence. And Shannon compression theorem says that there is a code in which we can achieve a rate of compression, which means that the number of uses of the channel will be n times r. That is exactly equal to the entropy that converts to the entropy in the asymptotic limit. So that's the operational meaning of Shannon entropy. It's exactly this thing. Is the maximum rate at which I can compress information. And the converse theorem shows that this thing is optimal, which means that there is nothing you can do to do better than this. If you compress information at a rate smaller than this, you lose information. There is no way to do this. Because the compression information says that you just need to compress these things, the sequences here. But if you compress at a rate smaller than h, what happens is that you are compressing less than the typical set. So you are throwing away sequences that are overwhelmingly likely to occur. So you are losing information. That's the idea behind data compression. And you see that if this guy is uniform, if the probability distribution associated with x is uniform, then this guy is equal to this guy. And the typical set is equal to the entire set, and you cannot do this. Do nothing. So we cannot compress a true random variable. Not a true, but a uniform probability distribution. As I told you, the proof is divided into two, with direct coding that we proved last Friday, and the converse theorem. But that says that this is optimal. And both theorems, compression and data compression and channel capacity, both of them has direct coding, which shows in one direction that's possible to achieve that rate, and the converse theorem that shows that rate is actually optimal. There is no way to do better. So, and typical sequences are with that typicality that we just defined, you can prove this thing very easy. This one researches on some entropy inequality, but I mean it's also based here in the typicality, because everything is in the asymptotic limit. Okay, then we need two other things to prove Shannon capacity theorem. Because of this thing, we show typicality for the entropy, for Shannon entropy, but we have typicality for joint entropy and also conditional entropy, which is a little bit more delicate, but we need it to prove the Shannon capacity theorem. Okay. So the same thing, joint typicality. We can let two random variables now. Remember that the Shannon capacity, the capacity of the channel is defined as the maximum mutual information between the input of the channel and output of the channel. So we need two random variables. One in the input that Alice just pick up there randomly according to some probability distribution, the message that she will input at the channel. And then we have noisy channel. So noisy will generate some randomness, and we'll get an output of the channel a random variable y. That's also random because of the noise. So we let emit a bunch of sequence, a huge sequence that Alice puts everything in the channels, and then Bob gets this thing, and they want to know. Bob measures this thing, and he wants to get xn from these measurements. That's the idea of communication. And then we define the sample entropy of the joint probability distribution in the same way that we define it for the single probability distribution. And we define the typical sequences in the same way. I mean, the jointly typical sequences are those in which the sample entropy is closer to the true entropy, the joint entropy of the series. Always the same thing, and the typical set is defined in the same way. Okay. Here there is a thing here that we didn't put there, because in the entropy here, this guy is always in the typical set. Here, we are assuming that the individual sequence, because here the typical sets are the two sequences belonging to the typical set, the joint sequence. Here we say that each individual sequence belongs to individual typical sets of the two random variables. It's a stronger assumption. Can you see? It's a stronger one. So I'm putting these here because the proof of these relies on strong typicality. But when you prove strong typicality, you prove that this is true, and you don't need this thing. So typically, the joint sequence will be composed by sequences that are typical. It's a stronger statement. But you can prove this. I'm just putting this here. It's not necessary, actually, because with strong typicality, you can prove that this always happens.
You mean that, so you're putting it, but is it strictly necessary? So is it adding like new constraints, or just imposing joint typicality, it also imposes that sequences?
No, it's because to prove this, to prove that these converges to this in probability, you need this and this. In the middle of the proof, you
okay,
have to
but
do
then
this. So,
that second part is redundant, right? If you already assume that those two things are close.
oh, no. I'm not assuming that it is close.
I mean, in defining the set, defining the jointly typical set.
I'm just defining the typical set. The typical sets are those in which these guys closer to this guy. Mm-hmm. And then you prove in the asymptotic limit, like you proved here. Let us go to just one. We define the typical set like this. When this guy is equal to this guy. I just defined it, this guy. I mean, I can define whatever I want. It's, I mean, I call this thing typical. It doesn't matter what typical means. And then this is just the definition of a typical the set. This is the typical sequence, that's the typical sequence. I define it like this. But then, these are the properties of this guy. Then you need to prove these properties. You need, Then you go to infinite limit and you prove that this thing happens. So the asymptotic equipartition property. Here we do the same, but we prove, we define this thing, this set, but then to prove the property, we need this. But then when we define strong typicality, we see that this happens, and we actually don't need to assume this. This actually happens. Is that clear? I don't know. I mean, you can just raise your hands and talk to the microphone. To prove these properties here, we need that thing. Otherwise, we cannot prove. So they fulfill the same properties. I mean, the probability of the joint sequence to be in the typical set, jointly typical set, converges to 1 in the same way as the probability of the just 1. So we expected this because we can think about this probability as a joint one, a single random variable. And then the same thing happens. We can bound this thing, but now with the joint entropy, exactly the same way we did with the typical set for a single random variable, and the equipartition also holds. I mean, the probability of this joint sequence to be in this typical set is uniform. I mean, every joint sequence in the typical set has the same probability in the asymptotic limit. So to prove these things, we need to assume that thing. But then when we go to strong typicality, then we don't need to assume that thing anymore, and everything is proven without that thing. But anyway, until now we have to put that assumption there, otherwise it's impossible to prove. But it's expected to do this, because you can simply ignore one of the random variables, and I expected that the other one will be in a typical set. I mean, intuitively I expected this. I just throw away one of the random variables. This cannot move the other one to the atypical set. Typically, intuitively speaking. So we have this exactly the same thing. That's the product of the marginals, with the size of this guy is equal to this guy, because the size of the typical set is equal to the n times the entropy of each one. And that's the joint typical set, which is even smaller. So, and that's the total number of sets, so it's huge. When we were discussing Shannon capacity theorem, we used this thing, because we said that both of these sequences, X and Y, should be in the typical set. Because Bobby was trying to understand just the typical set. That's the joint typical set. And then we use a different thing to prove the convergence of this guy. Not the convergence, the range. Do you remember what was? I think that he asked me yesterday. The conditional typicality. Otherwise, you cannot decode the information. And that is what limits the rate of communication, conditional typicality. We cannot do better than this. So, conditional typicality is a little bit strange, because we are saying we are conditioning the information on Y, given we know X. And this given we know has deeply different meanings in classical and quantum systems. Because To know quantum systems, we need to measure quantum systems, and then we need to perturb quantum systems. So this changes a bunch things. So this holds for classical typicality. The other ones hold for quantum typicality also, a little bit different language, but here is just for classical typicality. We have the notion of conditional quantum typicality, but it's a different thing. We will show this tomorrow. So conditional probability is defined like this, and then we define the conditional sample entropy, which is the entropy of the conditional probability, as usual. So this is the how much information I can by upon learning about y upon learning x on average, and then assuming the same hypothesis, identically distributed probability distributions and independent ones, I can simply write like this in the same way we did the probabilities, and then we do everything in the same way. The proof of these three typicality are basically the same. I mean, you can prove just doing the same. The properties of these typical sets are proven in the same way. Then we define the conditional typicality in the same way. We say that that are those sequences in which the conditional sample entropy converges to the conditional entropy. Okay? Always in the same way. And then we prove things, but now is a little bit different because here, unity probability is on average, because we are averaging over x. Because every sequence in x will give me a different information about y. So we need to average over all this to get the expected probability. That's a delicate thing that you have in conditional probability, because we are saying that we know some sequence. So on average, we expected this to happen. On average, we have a sequence in y space that will belong to the typical conditional set. That's fundamental to prove Shannon's theorem. The rate of Shannon's theorem. Exponential cardinality, we see that's different. It's asymmetric, because in one direction we have this thing, it's easy to prove, but in the other, we have to average overall input sequence. So just the expected length of the conditional set is this guy. Is bounded from above by this guy and below by this guy exactly. Okay? That's the difference, the main difference, because we need to average over the input sequences to ask about, in general, on average, how much information I'm going to get. Equipartition is the same. Then it's the same thing. Equipartition is exactly the same. We can always prove this thing. You just change this guy and this guy. And it's just, I mean, the proof of all of these properties follows from the application of the law of large numbers. So the equipartition, in this sense, asymptotic equipartition property, which is the naming of all of these properties, is the joint name of all of these properties, is basically a restatement of the law of large numbers applied to probabilities. It's just this. This leads to this very nice things that we can use it to prove Shannon's theorem. And remember that the conditional set, to prove the Shannon capacity theorem, we have the set of all sequences, and we have the set of typical sequences here. The set of typical sequences are those that Alice will typically input into the channel. Okay, and then we have, remember that each one of these sequences is some message. It's very huge. And then we have here the typical set that's not shown here. But inside the typical set of this variable here, we have the conditional typical set that says that this guy will be mapped to this guy by the channel, to this small set here by the channel with high probability. So we simply divided the typical set by the number of messages, and you have the number of conditionally typical sets. And then what you have in the exponent is just the number of typical sets is the entropy, and you have the joint entropy and the conditional entropy here. And this is exactly the mutual information. That's why the mutual information appears here as the maximum rate of communication. Because of the conditional typicality. If you split the typical set into a bigger set of conditional typical sets, what's going to happen is that these guys will start overlapping. And then Bob cannot uniquely decode the sequences. And this is a bad code. Because a good coder needed to encode and then uniquely decode. Otherwise, I'm losing information. So that's why the mutual information appears here. That's the main idea. Strong typicality. Strong typicality will not prove these things because it's much more complicated, but the idea is that it's very easy. Typicality, weak typicality, we impose it at the sample entropy, which is an average, converges to the entropy, the true entropy of the source, which is also an average, because the entropy is just an average of the expected information that you have. Here, this is the number of times the letter X appears in the sequence xn. Yeah, this notation is not good, but X is one of the letters of the alphabet. Xn is the sequence. So this is just the number of times that the letter X appears in this sequence, specific sequence. When I divide this by n, this is just the frequency. So I have a bunch of, I toss a coin several times, count the number of tails, and divided it by the total time that I toss the coin. This is the frequency of tails. So strong typicality demands that this guy converges to the real probability, which is a much stronger statement than imposing that average converges. And of course, this guy, strong typicality implies weak typicality, but the opposite is not true.
The number of letters that will appear n times the probability, you are using strong typicality, not weak typicality there. No?
Oh, no, not really, not really. I mean, we expect this to happen, but that is not, I mean, we're not demanding this. We're just demanding that the things go to each other on average. So one probability can convert, the other cannot. But the strong typicality, we demanded that every probability converge to the real one, which is different. Because, okay, we put that thing, the number of letters there, but then we put that thing on average. Inside average, we computed the average. And we demanded that the average, which the entropy, converges.
What was the average?
Well, because of this equation. This equation. This guy, what appears here when you do the calculation.
But I mean in the previous.
Yeah, but I'm using this guy here. Because you put this guy here, and then what appears here is n over it's the number of times the letter AI appear in the sequence divided by the total number of things. This is the frequency, yes, but I'm not assuming that every one of these guys converges to every one of px. I'm assuming that this sum converges. I can have different probability distribution that converge to the same sum, the same number. You see? Yeah, because I'm assuming that this sum converge. Strong typicality, I say that every one of these numbers are equal.
So if I understand correctly, what you mean is that you can go you can do this without the previous, because the previous one is a strong typicality, no? The previous that the Px, x1, x2, and xn is approximately equal to Pxa.
Yeah. This is strong typicality.
But if you can, what you mean is that you can go, you can get the approximation there in the second equation without using the previous one, actually.
Well, you don't need to use this thing, but
Okay.
you can prove different. But the problem is that I don't expect that this guy is exactly equal to this guy. What I expect is the product is equal and this is equal. This sum, the average is equal. Because this thing is just the average of this guy. So I expect that on average, this guy will be equal. That's a weaker statement that I say that every one of these numbers are equal to the true ones. But I mean, we expected that this is true when we do many measurements. I mean, go to really and go to infinite, we expected this. At least we assume that this is true, unless comparing experiments with the theory, we assume that this is true. Otherwise, it makes no sense for us. No? Yeah. So that's on average, and here they assume that the frequencies converge exactly. So it's a much stronger statement. It's more difficult to prove the properties of this set, but the set has the same property. They go to unity probabilities, exponentially small cardinality, and equipartition property. They fulfill this, and this guy, of course, this guy implies weak typicality, but the opposite is not true in general. And then the channel capacity, that's just, the maximum mutual information, which is this guy here, is equal to the capacity of the channel. That's channel entropy, and we need to join typicality because of this guy is a joint probability distribution. So you need to prove, and you need conditional typicality because the channel is described as a conditional probability distribution. So I want to know, given that I have how much information about y x has. Okay, that's the mathematical description of the channel. And the proof, of course, contains two parts. The first one, which is based on this typicality argument, shows that you can actually achieve this rate of communication. And the second one shows that this thing is optimal. The second one is more complicated to prove, but it's also possible to prove, and prove the optimality of the communication rate. So, and this is because, just counting sets, because we got this number, just divided the typical set in Bob's side by the number of messages, and then he defined the number of conditional typical sets, because he needs to distinguish between the messages, and distinguish between the messages. The only way is if each message is mapped to a disjoint subset in the typical set. Otherwise, we cannot distinguish between that. And then Bob could not decode the information. That's why the mutual information appears here, and that's why you cannot do this. Intuitively, you cannot do better, and then you can prove that the converse theorem proves that this intuition is actually correct. It's impossible to do better than this. That's the maximum possible of information that any channel can send. And this is interesting because it only depends on the probability. This guy you get experimentally. You just test the channel and you get this guy experimentally. It's almost impossible to do this beforehand. But experimentally is easy. You just throw known things there and measure the output, and you characterize the channel. You have this conditional probability distribution. This can be done everywhere. For instance, in a quantum computer, you can think about it as this guy, because you have an input that you consider that's pure state, getting into, and then you have some computation that's supposed to be unitary, but it's not because there is noise. And then you have the output. So it's a communication process. And you can characterize the noise in the quantum computer by measuring these things. So you throw known things there, and you do known operations, and you expect something there. By the difference between these guys, you characterize this probability distribution. And then you can, in principle, you can compute this thing. But it's extremely hard to compute, but we can use whole levels bounded to upper bound this guy. Okay, that's Shannon theory. Oh, okay. Questions? Because I mean, this is classical typicality. All the classical information theory is based on these things. So, if you understand that this idea, the rest is easy to understand why these limits in communication actually exist, and you cannot do anything to violate these things. It's really impossible. It's not a matter of being clever or other things. Of course, you can use resources to improve these, like you can use correlated inputs into the channel. So violating this hypothesis. So this thing does not hold anymore, and you can increase it. We actually do this. We use entanglement to improve communication capacity. But then to create entanglement, you needed to invest energy. So it costs more. That's the point. Because what we need is to minimize the number of times we use the channel. Because actually it's usually expensive to use the channel. So you want to use less. Like a radio station. Radio station uses electromagnetic waves to transmit radio waves. But then it has to invest energy, electric energy, in order to generate the waves. So somebody has to pay the bill. If I can use less energy, it's better, because I make more money in the end. And this is why we needed to. That's the way Shannon was thinking, because Shannon was an engineer. So it's applied guy. Has to solve a problem for the company, which is IBM. He was working in IBM, so he has a problem. Let it solve a problem in the way I will make IBM to save money. That's the idea. Yep. And that's it. Yes. Okay. I would like to show another thing for you, which is not because of the physics behind this thing, but because there is a different sort of entropy there. That's very useful for some problems, especially for Gaussian problems. I'll talk about a paper that I published with Miko some time ago. And the physics here is not that important, but try to focus on the definition of entropy that you put. It's a different entropy that can be useful for very, very different perspectives. So, talking about equilibrium phase transition that I think everyone in this room knows about. No? Statistical. When you do statistical physics, a fundamental quantity there is the partition function. So if you compute the partition function, we can compute everything else from the partition function. So it establishes everything. We can compute every thermodynamic potential. For instance, Helmholtz free energy, which is just written in this case. So every potential appears as a log function of this guy. And this is where phase transition is defined, at least the first order phase transition, equilibrium phase transition for now, that the thermodynamic potential become non-analytic in exactly the point of the phase transition. So everybody knows this. This is very nice, a very beautiful subject. I really like phase transitions. It's beautiful phenomenon. I like nonlinear phenomena, phase transitions, and things like this. They are really beautiful. Quantum systems. Quantum systems, there was proposed a new kind of phase transition. It's called dynamical quantum phase transition. In a bit, I'll show the reference of the guy that proved this, that proposed this. And it happens like this. The system is preparing the ground state of some Hamiltonian. So I just prepared the system there. the ground state of some Hamiltonian. So, and then I change the parameter of the Hamiltonian by I do something. For if this is a set of spins, I just change the magnetic field that I apply on the field, or turn on a magnetic field, or turn off a magnetic field. Just this. Physically speaking, is this. And then I change the parameter from some initial value to some final value. It can be a set of parameters also, doesn't need to be just one. And the Hamiltonian changes from A naught to A final. Okay? This basic thing is we call this thing quench. When you quench the system, you just hit the system with something. And then you just compute the evolved system. The evolved ground state of the system. The ground state with respect to A naught, you evolve with the final Hamiltonian. So that's basic thing that we do. Okay? And then we define what's called I learned very recently that people from condensed matter physics doesn't like to call this Low-Schmidt echo. I don't know why, but they simply don't like. I said, okay, don't call it Low-Schmidt echo. But I'll keep calling it Low-Schmidt echo, which is just the fidelity that we defined yesterday. It's the fidelity for pure state. We just defined this thing yesterday. It's the fidelity between the evolved state and the initial ground state of the system. Nothing more than this. If the ground state is degenerated, then we can define the total probability of the system at some later time in the future to come back to the ground state manifold, which is just this guy. Okay, easy, easy, easy.
In that case, how do we define the initial state if there is degeneracy?
Well, it's a general superposition of all the ground states of the orthogonal rotation. Let's suppose that you have two degenerate ground states. The ground state is doubly degenerated. You just can define the probability of getting in one or in the other. Mm-hmm. Because this expands the entire Hilbert space, this sub-Hilbert space.
You mean probability in the classical sense, so it's a mixture.
Oh, it is. This is the amplitude probability of psi. If this guy is 1, then these guys are equal. Okay. It's the fidelity, just the probability the way we do in Bohr's rule in quantum mechanics. Just the fidelity. So Low-Schmidt echo, what you call is the probability of returning to the ground state manifold. That's the meaning of this guy here. So why we are defining this thing? Because a guy called Markus Heil, a German guy that's working in Munich, if I'm not wrong, if I'm not mistaken, he realized that this guy has a formal equivalence with the partition function. And then he proposed the thing. Because that paper here, Markus Heil, Pokovinikov, and Karim, they published this thing in 2013 and proposing this sort of a phase transition in time. That I think that I'm interested now because of the properties of these guys. So they defined the rate function, which is just the log of L. They call this the rate function. They realized that this guy in time has some kinks. And these, well, it's not because it has kinks, it's not because it becomes non-analytic here that we have a phase transition. We have to have some other things to confirm that this is indeed a phase transition. It's not because the function is non-analytic that we're talking about phase transition. It's a little bit more complicated, and the reason why they call this phase transition is this. Think about you have a partition function that's bounded by some state. This is called in statistical physics literature boundary partition function. So we just bounded the guy. So the Low-Schmidt echo, when I go to the imaginary axis of time, can be seen as a boundary partition function, but bounded by the ground state. I just put here, R is IT. This is just the Loschmidt-Chaco with the ground state. With the ground state here. Okay, psi is equal to phi, that's equal to the ground state. This R is equal to IT. This becomes exactly what we call the Loschmidt amplitude, sorry. No, that's the echo, that's the echo. Okay? So these guys realized this, and then they said, okay, let us go to the complex time and see what happens. And then it's possible to prove that we can write the Loschmidt-Chaco like this, which can be put like this. This is called the Fisher zeros or Young-Fisher zeros, because it was proposed by this guy here. And this is deeply related, the distribution of these zeros, the zeros of this function, these guys here, are related to the phase transitions in the way that I will explain now. But this is just, the guy realized that this guy is basically the Loschmidt-Chaco, the boundary. Loschmidt-Chaco plays the role of a boundary partition function, bounded by the ground state in the complex time domain. And then they just realized that, oh, we can study Fisher zeros of this guy. And this is a complex function, you can write it like this, and study the distribution of these guys. So, what you have in a regular partition function, what happens if I go to the imaginary time domain, just do a linear rotation, and plot the distribution of the zeros of this function in time, they will accumulate. That's what Fisher and Lee and Young proved. They will accumulate on a line or on a region in the infinite limit of the thermodynamic limit. When I go to infinite size of the system, they will do this. When a phase transition happens, when this line touches the real axis, or this guy touches the real axis, that's where a phase transition occurs. In the equilibrium case, we do the same thing, but we do a Vic rotation of the system. We go to the imaginary temperature plane. So you have the imaginary temperature here, the real temperature here, and you compute the Fisher zeros of that function. Exactly in the same way. I mean, you just pick a beta and go to imaginary temperature. So you have a partition function that's imaginary. And then you plot the zeros of this guy, and when the beta touches the real zero, the zeros of this function touch the real line, that's the critical temperature. That's where a phase transition occurs. And they show that the same thing occurs in time. So the distribution of Fisher zeros accumulates on a line or in an area, depending on the system that you have. And when this guy touches here, you have those kinks in time. So that's why they call this phase transition, because of this property here. Okay? So in the infinite time, you have a line. Sorry, not time. In the thermodynamic limit, when the size of the system goes to infinite, those distribution converges to continuous distribution. And you have phase transitions when these guys touch the real time. So you have phase transitions in time. Because not just because the Loschmidt-Chaco becomes zero, so the rate function is non-analytic, because the log of 0, but because the distribution of the Fisher zeros touch the real time axis. That's why we have phase transitions. That's why they call this phase transition. Dynamical, because this happens in time and not in equilibrium. So the question that we are interested here is, let us study the entropy of this guy. What happens with entropy? But the problem is that thermodynamic entropy, well, I cannot define thermodynamic entropy here because it's out of equilibrium. So it's not that easy to define these things. And then we think, let us study some known entropy that comes from phase space of quantum mechanics. Let's study what happens there with this thing. So we pick up this model. The results that I will show is independent of the model, but we pick up this model, which is a very famous one. So this is the angular momentum of think of a big spin, and you have the angular momentum in that direction, which is the quantization axis here. And we have this jx squared, with the operator in the x direction. This means that just we have a precession, we have a thing that's precession, an angular momentum that's precessing with this frequency here, and now it's compressed in the x direction. So it's doing this. It's processing being squeezed in the x direction. That's what we are doing with the angular momentum here. So this is just a squeezing thing. And this model was proposed by these guys here many years ago. It's extremely well studied model. And what happens in this model that is interesting is that you see a critical line here. These are the Young values. This is a function of age. So you see that this thing is here, from this point to this point. Here the spectrum is doubly degenerated. Here is not. This is the symmetry behind this phase transition. Because every phase transition is related to some symmetry change. Or a symmetry appears or a symmetry disappears. But something happens with symmetry of the system. This is just the degeneracy of the system that changes. Can you understand that this is the side question is not important to understand it, but do you understand why this is a symmetry change? I mean, which kind of symmetry is being changed here? What? Okay. Okay. So it's just a symmetry that's being changed. Just for you to see, we pick up the time average magnetization of the system. So just compute the spectral magnetization average over time. And you have this thing as function of age. Age is the parameter here. You see that it averages to a finite number up to here. If you increase the number, the dimension of the system, which means increasing the value of this guy here, j, small j, this guy goes to, every time it increases, it goes to more strong change, which means that average to some finite system, finite number here, and here is 0. So that's the critical point of the model. So this is what we call order parameter in phase transition. It simply changes the value in which it averages when you cross the critical point of the system. This is very known for many decades, actually. And that's the Loschmidt with the size of the system, how it does change, actually. It goes like this, so it decreases. There's amplitude decreases, but it oscillates. But that's okay, Loschmidt oscillate. What happens is that these happen. So, at these points, that's the rate function, basically the normalized log of the other plot. So here is numerical problems, because it's very close to 0, so the computer, but at every point of these things, these are called the critical times of the system. These are the times in which the Fisher zeros touch the real line, the real time axis, and where we have the phase transition, the dynamic of phase transition. These were supposed to diverge, but of course, numerically you cannot diverge, it keeps like this. It keeps diverging, but decreasing the size of this guy, which means that it probably thermalizes. R is this guy. So when the Loschmidt echo goes to 0, R, and Loschmidt echo goes to 0 when the system comes back to the ground state manifold, and it happens that this guy touches the real axis. So we have a phase transition there. That's what's called a dynamical quantum phase transition. We don't know the relation. People start thinking that this is in some sort related to the equilibrium phase transition, but then they realize that they are not related. And now people are studying the relation between these guys and excited state phase transition, because it is a phase transition that occurs in excited states, not only on the ground state. But the problem is that people still don't understand too much of this thing, and they do not understand the exact relation between these guys and symmetries. So people are studying these things. It's a very nice thing to study. But the entropy. So we know that that was the quantity that we choose to study this system, instead of the thermodynamic entropy, because we don't know what to define for non-equilibrium systems. We study these things. We know that in classical phase space is okay. We can build classical phase space very easy, but quantum mechanically we cannot. There is no phase space in quantum mechanics. It's impossible to build a phase space in quantum mechanics. Okay, because array in Hilbert space cannot be represented by a probability distribution, but it's represented by infinitely many probability distributions. So we cannot build phase spaces like this. But we can build quantum phase spaces, which are very useful tools, extremely useful tools to study, especially Gaussian systems. It's very easy to deal with these guys. But we can use, people from quantum optics use phase space description of quantum systems very often. I mean, probably you know a name, Roy Glauber, no? Yes, a Nobel Prize that got the Nobel Prize because of the description of electromagnetic field in phase space. He basically invented coherent states and things like this, which is this one. So this is the Husimi function. I don't know if you heard about these things. It's just, this is the density operator for the system, and this is the coherent state. It can be defined for anything. For instance, the electromagnetic field, this would be the eigenstate of the annihilation operator. So we just pick up the coherent state here, coherent state here. So it's the coherent state representation of the density operator. That's the Husimi function. At some books you see 1 over pi here, just to normalize, but anyway, it's just a constant. I prefer not to put it. But what turns out is you can actually define coherent states for spins. And it's defined like this. Think about the Blois sphere. If you have a Blois sphere representing this guy, this angular momentum, then you are just pick up in the maximum one, the maximum projection of the angular momentum, and you are just rotating it over all the Blois sphere. So that's what you call coherent state, and why we call coherent state of the thing. Because these angles, phi and theta, when you take the limit, the thermodynamic limit, these guys, the expectation value of the angular momentum, respect to this thing. So this is like the classical angular momentum. But this is not a vector. I mean, we know that the 3 components of the angular momentum doesn't form a vector. The angular momentum is an algebra. But in the classical limit, in the same classical limit, when the size of the system goes to infinite, these guys behave like this. So that's why these states are called coherent states, spin coherent states. And we can use this to analyze any system we want. But this is the limit of J going to infinite. Okay? So that's the Husimi function. It looks like a probability distribution, but it's not. Okay? The Husimi function is normalized. The integral is equal to 1. It's bounded between 0 and pi. In the way I defined it here, it's bounded between 0 and pi. If I normalize it 1 over pi, so it's bounded between 0 and 1. And we can take, so it's normalized. I can compute average of operators, like multiplying this guy by the representation in phase space of the operator. Which I can build the representation. If I put a J here, I can build the representation of J in the phase space. That's easy to build. And then I put the representation here, and I get the expectation value of J. So you see, though, this looks like a probability distribution, but it's not because the marginals are not correct. Like in Wigner function, when we define it, you have a negative probability. P function by Glauber, we have a divergence. Any quasi-probability distribution that we define in phase space has some problems. And this is because we cannot define probability distributions for quantum systems. That we have to pay a price. But these are very nice tools because, I mean, if I can put any operator here, and then I have the phase space representation of this operator, and then I compute expectation value like multiplying by the Rossini function times the representation of this guy in phase space. This is exactly the way we compute expectation value in classical statistical physics. We just need to take care that this is not a real probability distribution. So, and then we define this entropy, which is called I don't know how to say the name of this guy. Maybe he does. Sorry, come again. Okay, I cannot repeat this, but is that name? That's the name of the guy. Okay. He introduced several entropies with this form, and this is the specific one for the Rossini function. In the end, this is information probability because this is supposed to be probability distribution. So this is the Shannon entropy of the Rossini distribution. This is exactly this. What happens? This is just normalization factor. It doesn't matter. So, but this is the Shannon entropy of the guy. This is exactly the Shannon entropy. And then we are interested in the rate of change of this guy, that we split it into this guy here. That's why we and you see, this is 1978, the paper. The Reviews of Modern Physics is very nice about general properties of entropies. Actually, this is a very nice reading. He defines entropy in general with an F here, which can be any probability density, or any function actually. And then he studied the general properties of these sort of functions. It's a very nice reading. And then we just computed in this paper here. We computed the way these guys changes. I mean, just increasing the number of things. We see that the entropy oscillates. If this was the thermodynamic entropy, it could not oscillate because it can increase. Thermodynamic entropy always increases. This guy is decreasing because it's oscillating, so it could not decrease. But we see that on average, it's increasing when the size of the system increases. And this is strange because I'm very interested in the properties of this guy that makes quantum systems look thermal. And I cannot link this guy with thermodynamic entropy or thermality because these guys are different. This is an informational quantity. But this means that information is being spread in the system. And when we increase the system, it's being spread a lot when we increase the size of the system. So so from a point of view of an experimentalist, information is getting harder and harder to get back. You have to measure more things. And this is that pi, which is the derivative of that guy. So you see that becomes negative, but that's okay because it's not the thermodynamic entropy. So and we are out of equilibrium. We don't expect that it is to be positive. But I mean, it oscillates, this guy, when we increase. And that's the main thing, what we plot here. These are the critical times, the times in which the rate function diverges. And this is the maximum of the entropy production of these guys here. So when I increase the size of the system, these guys converge to a line, which means that entropy production, this is not 45 degrees, so the maximum of entropy production occurs a little bit further than the phase transition, but it starts increasing when we get closer to the phase transition, and then increases a lot, and then the phase transition occurs, increase a little bit and decrease, and goes to zero. That's why that these sort of things happen. So information keeps coming, oscillating in this way, but it tends to go. It tends to stabilize to a number. So, and this, we expected this because, I mean, there is a maximum of this guy. This guy cannot increase forever because the dimension of the Hilbert space is finite, so it cannot grow forever. It doesn't need to grow, but if it grows, it has to stop at some point because there is a maximum of this guy. My channel entropy is bounded. If the system is bounded, channel entropy is bounded.
There is something that I don't remember very well, because it wouldn't be, because I understand that this line in the critical times is expected somehow, because essentially the Hamiltonian, the norm of the Hamiltonian also depends on J. Because
Also depends on
J, on J.
Ah, yeah. It depends on J here.
So I don't remember if we normalize it or not.
Yeah, we normalize it.
Okay, perfect.
No, we normalize otherwise.
Otherwise, it would be
It's
artificial.
Otherwise, things would be very, very different. Yeah, we normalize it. Okay, so that's the main result. You have this thing, but the entropy tends to stabilize. Not when the system is small, that the entropy keeps oscillating here, but it's not stabilizing. We don't know if this is the maximum or not, but I mean, it tends to stabilize. What does this mean? Well, this means that this information was spread in the system and cannot spread more, which means that the system occupies all the Hilbert space. And we actually did some semi-classical approximation there that is used in the study of equilibrium phase transition with the hosted Primakov approximation. And we saw that this is not enough to understand this thing. We need because this hosted Primakov approximation, it stays closer to the low energy levels, which is close to the ground state. But this guy needs the entire spectrum to be explained. So it spread all over the Hilbert space. And this is a thing that I would like to understand better, actually, why this happens. And then I promise you that I will finish him before the Q. Yeah, before the Q. That's very nice. So a phase transition can occur dynamically in time, which is a very nice thing. There are plenty of things to study there. There are people trying to simulate this in quantum computer, but it's very difficult because one thing, you need to follow the evolution of the system for a long time. And this is hard to do because of the coherence. This is actually very, very, very hard to do. But if you can do this, then you can. I think that a few people did it actually this in ion traps or things like this. So entropy is not always positive because we are out of equilibrium, and that thing is entropy production. Sorry, the derivative. Entropy is always positive. That quantity is always positive, but the production not. It's the derivative. And we have this phase transition, and this apparently this goes to stabilization of information spreading over the system. In order to investigate this, we did these two papers very recently, I mean, this year. And this one, we actually computed how far from equilibrium you are. So you're able to compute the change in entropy, thermodynamic entropy of the system, by computing the distance using relative entropy. We are able to compute the distance from the equilibrium manifold, and then we computed how much entropy is generated in time by this guy. And it has the same behavior. I mean, entropy is always generated in the system because it's a many-body system that's interacting. So entropy is being generated there by free evolution. But the problem is that when you cross the phase transition, the the rate at which entropy is generated increases exponentially. We don't know why, we just see this. And here is a very nice thing that is a complexity quantity that we use here that's called the Krylov complexity. A bunch of people are using these things. Krylov complexity is defined here, we defined it there. It's a very nice thing that people started using this thing to study information black holes. And they realized that, oh, this could be used to study chaos. And then people started using chaos. And now they're using in a bunch of other things. That's the name of the thing. Krylov complexity. And then they extended this to quantum fields and other stuff. And recently, a guy published some paper that I didn't read yet, but something related to Krylov complexity and Nielsen complexity. Nielsen complexity is the complexity of quantum circuits. It's how complex is a quantum circuit to produce a quantum state in a quantum computer. It's a Nielsen complex. Apparently, the guy linked this to the Nielsen complexity, but I didn't read the paper, so I don't know. But it's very recent, I think, this year also. I think I don't know if it was published yet. I saw it on archive some other day. So, and these guys show the same behavior. I mean, complexity increases exponentially fast when you go to the phase transition. And in this paper, using that model over there, we show that the Krylov complexity is another parameter of this transition, and that the gauge entropy that I spoke with you today, yesterday, is actually equal to the Krylov complexity. So for some reason they are equal. We don't understand why, but the result is there. And the entropy looks to reach the maximum, but we're not able to show that, mathematically show that this actually is the maximum possible entropy, but it looks like that's reaching the maximum entropy, which means that these sort of things could lead to thermalization. And we are using, relative entropies, complexity to study these things. So that's why it's important to understand these tools, because even if you don't want to work in information theory, which I don't like too much to work in proper information theory, but the tools are amazing. You can use it everywhere, these things, to solve other problems. So we just need to understand it from where they come and to understand how to apply these things. That's the important thing. And that's it, guys. Questions? And that entropy can be defined for any other function. There is a very nice paper. The guy defined it for Wigner function. The problem is that Wigner function becomes negative, and then that entropy becomes complex. And then comes the question of the meaning of complex part of the entropy. There is a paper recently published in one of the physical reviews that discusses the meaning of the complex part of this thing, and apparently it's linked to dissipation or something like this. Oh, sorry, dissipation, with the generation of coherences. Because when you generate coherences, Wigner function starts oscillating and starts becoming negative, and the negative parts of this thing reflects in the complex part of the entropy. This is.
But for instance, if you have focus state 1, this is also negative, and there are no coherences because you have a single mode, no? So what this means then?
When the Fock basis.
Yes.
Well, okay, you're right, because coherence depend on the base. But Wigner function, it doesn't mean that you have coherences in one base. You have a Wigner function that's positive or negative. This doesn't mean, yeah. I mean, we know that for Gaussian states, We can have coherences in some other bases, but a Gaussian bigger function is positive, always. So that is, but they related to generation of coherences in some way. The negative, the imaginary part of the entropy. I didn't read the paper, but I know that they relate. I don't know which relation they built.